Academy. Today we'll be looking at extractions of metal. Remember this part 2. In part 1 we studied metals from the periodic tables, and we've looked at transition metals. So in this second part 2, we'll be looking at the extractions of metals, but we've most likely focused on iron, extraction of iron from hematite, and the extraction of aluminum from bauxite. Okay, from the ore called bauxite. So, without much ado, let's begin. So this is part 2 of what we have today, of what we have for this chapter. Now let's take a look at the extractions of metals. We say that the earth crust, this earth that we are, contains a lot of metals, and not just metals and their ore, metals and their metal compounds. Now, some of the minerals or metals that are found on earth is the gold, copper, iron oxide. Iron oxide is especially iron 3 oxide. Okay, especially iron 3 oxide, right? Iron 3 oxide, like we have copper, we have gold, we have iron 3 oxide or iron oxide. Iron 3 oxide is the all of iron, and we have aluminum oxide. So these ones are the ones especially iron oxide, aluminum oxide, the one we want to focus on for this class, right? Now, metals are very useful to us. Okay, they are very useful to us, and we don't easily find most of the metals from the earth crust as metals. We don't easily find them as metals. We normally find them in a combined state. That combined state is called the ore. Maybe metal and oxygen. For example, you say iron and oxygen is iron 3 oxides, aluminum 3 oxides, and so on and so forth. So they're always in combined state. They chemically combine with oxygen or other metals, and we have to extract the metal we want from the compound itself. We have to extract. So even though the metals are naturally on earth crust, we don't just dig the earth crust and we find the metals. We have to extract them from their combinations. One of the methods we use to extract the metals is the electrolysis method. Now, electrolysis method is used to extract metals in the most reactive metals. For example, in the reactivity series, the first 5 metals in the reactivity series, first top 5, like you have the potassium, the calcium, the sodium, calcium, magnesium, and aluminum. Those ones, those very high ones, I think aluminum is not part of it. The first 5, aluminum is not part of it. So those first 5, we use the electrolysis method to extract them from their ore. The next one, like the aluminum, like the zinc, like the iron, aluminum is part of the first 5. Then the other one, the middle one, like the zinc, the iron, and so on and so forth, those ones, the copper, those ones we extract them using reduction with carbon. Reduction with carbon. So those middle ones, we extract them using reduction with carbon. And the last one, which is gold, we just dig and get. The gold is in pure form. It's not reactive. It doesn't react with oxygen to become gold oxide. No. You just dig the ground, find gold, you clean it, and you use. Okay? So we say most metals have been extracted from their ore using the electrolysis method. Okay? And using a blast furnace or by more reactive methods. Okay? So in the electrolysis method, either we use the blast furnace or reacted them with more reactive materials. Okay? Now let's go to the very first one that we want to consider for today's class. Okay? Now we say some of the good examples of the metals that we extract from their ore. The very good examples, some of them, is the iron and the aluminum. These ones are very famous metals that is obtained. And For the iron is obtained from its ore called the hematite. The iron 3 oxide is in the state of what we call the hematite. It's obtained from its ore as hematite, while the aluminum is obtained as what? As bauxite. It's obtained from bauxite, sorry, not as bauxite. It's obtained from bauxite. So aluminium 3 oxide is a bauxite, okay? So aluminium is bauxite, while iron is obtained from its ore hematite. We're going to describe how this works out, okay? Now we say that all reactive metals do not have to be extracted chemically, okay, like the gold, because they are uncombined with any other element, like gold. We already said this, okay? Okay, so we also say that this occurs as they do not easily react with other substances. Why? All reactive metals, you don't have to do anything. They don't combine with any other substance. So we just dig them from the ground and clean them. Then the middle metals in the reactivity series, after the first 5, they are extracted using reduction method with the carbon. Reduction method with carbon. Now let's take a look at the metals that requires electrolysis method. The first 5, 1, 2, 3, 4, 5. These ones, okay, probably with aluminum, extracted by electrolysis of multichlorides or multi-oxide. Large amount of electricity is required. It's an expensive process because electrolysis, you require electricity, the passage of electric current through an electrolyte. Okay, so all these first one, potassium, sodium, lithium, calcium, magnesium, and aluminum, you extract these ones using the electrolysis method. Remember that. We extract these ones using the electrolysis method, okay, the very reactive method. You know, after this one in the reactivity series, there comes carbon. There comes carbon. Now, then these metals, zinc and iron, they are extracted by heating with reducing agents such as carbon or carbon monoxide. So it's a reduction reaction with carbon. So when we want to do this, you want to extract zinc or you want to extract iron, you have to do a reduction with carbon. It's a reduction reaction with carbon or carbon monoxide. So we help you extract any of this one from their ore. Zinc blende. Zinc is from zinc blende. This one is also very significant for IGCSE. Zinc is from zinc blende, that's zinc sulfide. It's from zinc sulfide. While iron is from its ore called what? Hematite. Iron is obtained from its ore called hematite. Iron is obtained from its ore called the hematite. And what we do is that we react the coke. The carbon is from the coke. We react with oxygen to produce carbon dioxide. Carbon dioxide reduced with more carbon to produce carbon monoxide. The carbon monoxide we react with the iron 3 oxide to produce iron, and so on and so forth. Then we're going to take a look at this. Then the reactivity series after zinc and iron, we have hydrogen. Okay, remember these two, they are not metals. Carbon and hydrogen, they are not metals, but they are in the reactivity series. Found as pure element, copper may have to be extracted from its ore by heating with carbon or hydrogen. So this one, you heat it with carbon or hydrogen. Most likely silver and gold, they are found in their pure form. Okay, so that's the introductory part. Now let's go to the extractions of iron from the hematite, okay, which is the significant one that we need to take care. But before we do this, let's take a look at our tutorial. So we're looking at the extraction of iron from hematite. So we need to pay attention to this for Cambridge IGCSE. For this, we need 3 ingredients. 3 ingredients is what we need. Okay, if you want to extract iron, you need 3 ingredients. You need 3 raw materials. You need 3 requirements. The first one is called the iron ore, which is the hematite. The first one is the iron ore called the hematite, iron 3 oxide. The second one is the coke. The coke is actually the carbon. Then the third one is limestone. We need these 3 things to be fed into our blast furnace. We need these 3 things to be fed into our blast furnace. But before we do this, let's quickly take a look at our tutorial. Okay, so let's listen to our tutorial and see how
This
this
video
plays out.
is
Okay,
about the
thank you for
extraction of
joining.
iron from hematite in the blast furnace. Iron is extracted in a large container called a blast furnace from its ore, hematite. You need to know the raw materials that are put in the blast furnace, as well as the reactions that occur to not only form the molten iron, but also the reactions that remove the impurities. The raw materials are hematite, coke, a form of carbon, and limestone. Hot air is blown into the blast furnace to provide the oxygen. The iron ore contains impurities, so limestone is added to remove acidic impurities that will contaminate any iron that is formed. In Zone 1, the first reaction of this process occurs, which is simply carbon reacting with oxygen in a combustion reaction, which is exothermic, to form carbon dioxide. Remember, the coke is just an impure form of carbon. In Zone 2, more carbon in the form of coke will react with the carbon dioxide produced, and this will form carbon monoxide. This is an essential reaction, as carbon monoxide is the reducing agent for the formation of iron from iron oxide. Remember, a reducing agent will remove oxygen from another substance. In Zone 3, the carbon monoxide formed will reduce the iron 3 oxide and form molten iron. Carbon monoxide is therefore the reducing agent. The liquid molten iron is more dense than the impurities, so sinks to the bottom of the blast furnace and is tapped off. Remember, the molten iron is the bottom layer because of its density. There are impurities in the hematite which must be removed. These are carbon, sulfur, silicon, and phosphorus. Carbon and silicon are the most commonly asked about. The impurities first react with the oxygen blown in and form oxides. If the oxide is a gas, then it will escape out of the top of the blast furnace. In order to remove the acidic oxides, a neutralization reaction must occur. In order to provide an appropriate base for the reaction, calcium carbonate undergoes thermal decomposition to form calcium oxide and carbon dioxide. Calcium oxide reacts with the acidic impurities and will neutralize them. The reaction with silicon dioxide forms calcium silicate. The common name for calcium silicate is slag. The slag is less dense than molten iron, so floats on top and can be removed. Extended students should know the symbol equations for the reactions that occur in the blast furnace and be able to recall these in an exam. You can break these down into 4 parts. Zone 1, the combustion of carbon. Zone 2, carbon reacting with carbon dioxide to form carbon monoxide. Zone 3, the reduction of iron 3 oxide to form molten iron. And finally, the removal of acidic impurities. You must make reference to the impurities being acidic if asked about them in an exam. Let's now have a look at some exam questions. It is common to be asked how to remove the impurities from the blast furnace in an exam, as you have been here. Remember that the impurities have to first be turned into oxides. Stating this will score you 1 mark. Carbon dioxide and sulfur dioxide can escape as waste gases, but the oxides of silicon and phosphorus must be neutralized in an acid-base reaction. So for the final mark, you need to state that the acidic oxides, or you can name them, are neutralized by the calcium oxide, which is formed from the thermal decomposition of limestone. This question is for extended students only, as you have been asked for specific equations. You must name each raw material to gain 6 marks, and also state an equation for the reduction of hematite. The first part of this process is for coke to burn in oxygen or hot air, which has been blown into the furnace. This is an exothermic reaction, providing heat for the reduction of iron 3 oxide. Carbon dioxide will form carbon monoxide, which is the reducing agent for the formation of molten iron. Limestone has been listed as a raw material in the question, so you must say what reactions this undergoes. As we have looked at, the first is thermal decomposition, and the second is neutralization. Finally, there are 2 marks for the equation for the reduction of hematite. 1 mark for the correct formulas, and the 2nd mark for correct balancing. Don't forget that molten iron is formed, so the state symbol for Fe should be L for liquid. It is a good idea to check that you have covered what is being asked about in the 6 markers, so you could highlight or check off each point in the question. In summary, you need to know that the raw materials for the blast furnace are hematite, which contains iron 3 oxide, coke containing carbon, and limestone containing calcium carbonate. Carbon monoxide formed in the blast furnace acts as a reducing agent for the reduction of iron 3 oxide to form iron. Any acidic impurities are removed by a neutralization reaction with a base. And finally, extended students should learn the symbol equations for the reactions that occur in the blast furnace. Don't forget to check.
Okay, thank you. So this is the tutorial for this first part. Now let's take a look at it. It's broken down very well. Now we have 3 or 4 raw materials. Okay, the fourth one is the hot air. Okay, even though we didn't write it here, the hot air is also blown in. We have iron ore, which is called the hematite, Fe2O3. Okay, we call it iron 3 oxide. Okay, you have the coke, which is carbon, and we have the limestone calcium carbonate. Okay, this one we're going to heat it and it's going to decompose it to calcium oxide and carbon dioxide. Okay, now first of all, this whole blast furnace is divided into 3 zones. Okay, here is where we let in hot air. Okay, remember it's hot air. We let in hot air as the 4th raw material. Now that hot air react with the carbon from where? From the coke. React with the carbon from the coke. It reacts with the carbon from the coke. The hot air reacts with the carbon from the coke to produce what? To produce carbon dioxide. So carbon from the coke react with the air, hot air, to produce carbon dioxide. This is the first equation, and this is what is happening in zone 1. So carbon from the coke react with hot air, which is the oxygen from the hot air, to produce carbon dioxide. In zone 2, this carbon dioxide gas that we have produced, look at the equation here. Carbon, a solid, react with hot air, which is gas, oxygen, which is gas, to produce carbon dioxide. In zone 2, what is happening in zone 2 is that this carbon dioxide we have produced will react with more coke. Remember, we fed in this raw material from the top. Look at it. We let in iron ore to go in from the top. We let in coke to go in. We let limestone to go in. We let all this raw material to go in from the top. Okay, so they're already inside this place. Okay, now in zone 2, the carbon dioxide that we produce, this carbon dioxide, a good student will take note of these equations and every zone in the blast furnace. In zone 2, the carbon dioxide that we produce in zone 1 react with more carbon from the coke to produce carbon monoxide. To produce what? Carbon monoxide. Remember, carbon monoxide or carbon is a reducing agent. The carbon monoxide or carbon is a reducing agent. They will react with the hematite that has also been sent in to produce molten iron and more carbon dioxide. So in zone 3, what happens in zone 3 is that this reducing agent, carbon monoxide that we have produced, we now react with our hematite. You know, iron 3 oxide is a hematite, Fe2O3. This is the hematite, okay? Now this ore, iron ore, we react with the carbon monoxide we produce in zone 2 and reduce it. Why is it called a reducing agent? It will reduce iron 3 oxide to iron. This one will reduce iron 3 oxide, carbon monoxide, will reduce iron 3 oxide to only iron, and carbon dioxide will be formed. But you have to balance the equation if you want the full marks. Okay? How to balance the equation? The number of atoms in the reactor side must be equal to the number of atoms on the product side. Is that okay? For every element or for every atom. Okay, so that's that. Now you already have the carbon monoxide, which we produce in zone 2, react with iron 3 oxide in zone 3 to produce iron, multi-iron liquid. This iron is a liquid. Why is it a liquid? Because it's melted. It's melted. Okay, it's going to solidify later and become whatever it is, to become solid, and more carbon dioxide. Now at this point, carbon dioxide is a gas. So any impurity, like all this carbon dioxide, silicon dioxide, they are all impurity. Oxygen, all this impurity, they will escape here. If it's in form of gas, the impurity will escape. If it's not in form of gas, other things will happen to it. Now because silicon dioxide is not a gas, silicon dioxide is not a gas. You know, silicon will react, is one of the impurity. We react with oxygen to form silicon dioxide. Now this silicon dioxide, how do we get rid of it? It cannot escape. It's an impurity. Since it's not a gas, it cannot escape from the blast furnace just like that. It's an impurity. Even though it's an impurity, it's not a gas. You know, it's a gas that will escape, like carbon dioxide. If there's any other gas, we escape from here. As a waste product, we escape. But this silicon dioxide is not a gas, so it's not going to escape. So what we do is that, remember, that was the reason why we put why we put the limestone. Now this limestone, remember the hot air, the hotness of this blast furnace, we decompose this limestone. Calcium carbonate is a limestone. This calcium carbonate, we decompose into calcium oxide and carbon dioxide. We decompose into what? Calcium oxide and carbon dioxide. Now the reason why we fed in calcium carbonate is because there is an impurity we want to get rid of, which is silicon dioxide. The reason why we are putting limestone in this reaction, because otherwise you'll be wondering, what is the limestone for? We get it coke, we get white coke, we get white hematite. Why do we put the limestone, the calcium carbonate? First, we decompose it. The hot air we have, the heat, the thermal heat of the blast furnace, we have to decompose it to calcium oxide and carbon dioxide. Remember, carbon dioxide is a gas, so it's going to escape as waste, okay, as waste gas. Now, this remaining calcium oxide is a basic oxide, okay? All metal oxides are basic oxide. This calcium oxide is a basic oxide. So this calcium oxide will react with this silicon dioxide, which is an acidic oxide. This silicon dioxide is an acidic oxide and is an impurity. Now this impurity needs to be gotten rid of. So it will react with it to form what? To form calcium silicate. To form calcium silicate. So these two will react together. Silicon dioxide will react with calcium oxide, silicon dioxide, which is an impurity we want to get rid of, and we don't know how to get rid of it. So the reason why we put limestone is to break limestone to calcium oxide, and the calcium oxide can react with the silicon dioxide to form. This is a neutralization reaction, because this is a basic oxide and this is an acidic oxide. It's like a basic oxide react with acidic oxide to form calcium silicate, to form calcium silicate. This calcium silicate is an impurity that we need to get rid of. It's called slag. Now this slag can easily be gotten rid of, okay? The slag, calcium silicate, can easily be gotten rid of. It will exit from this place. We leave the blast furnace from this zone. Okay, now the multi-iron is denser, so it goes down. Below the slag. It goes down. So if they ask you what is a slag in a blast furnace for hematite, it's a calcium silicate. It's calcium silicate. We need to know that. Now this molten iron, which is liquid, is denser, so it goes down and it will be obtained from here. So you see, this is how we get the iron, the pure iron that we use for building the body of cars, body of everything we build. This is how we obtain the iron from it. Is that okay? So you can see the important reaction. The first one is carbon from coke react with oxygen to produce carbon dioxide is zone 1. The carbon dioxide react with more coke, more carbon from coke to produce carbon monoxide in zone 2. Then in zone 3, the carbon monoxide is a reducing agent. So it reacts with iron 3 oxide to produce molten iron and carbon dioxide. Carbon dioxide is a waste gas, it got rid of. And then we have many other impurities that are there, like silicon dioxide, because silicon will react with air to produce silicon dioxide. So how to get rid of silicon dioxide is that the limestone we fed in will be broken down because of heat into calcium oxide and carbon dioxide. Carbon dioxide escape. This calcium oxide react with silicon dioxide to produce a slag, which we now be able to get rid of. And the molten iron, which is denser, flow to the bottom, and it's obtained from here. Okay, so that's what we have for this. All this one is explaining the zone, what is happening. We've already mentioned them. We've mentioned them zone by zone, so I'll just show you the equation. But if you are extended, you have to know not only the symbol equation, and not only the word equation, you have to know the symbol equation. This is C plus O2 equals to CO2, carbon dioxide. In zone 2, like we said, the carbon dioxide will be reduced to carbon monoxide. Will be reduced by the reaction with another carbon. So carbon reacts with carbon dioxide to produce carbon monoxide, a reduction reaction. Okay, another reduction reaction. In zone 3, same reduction reaction will take place. The carbon monoxide that is produced in zone 2 will react with iron 3 oxide to produce what we call the iron and carbon dioxide. So produce iron and carbon dioxide. The iron is what we need. Okay, it's very dense, so it flows down. The carbon dioxide is a wasteful gas. It's got it rid of. Then we break the limestone calcium carbonate. It's called the limestone calcium carbonate. We break this limestone calcium carbonate into calcium oxide by thermal decomposition. You know, thermal decomposition, heat. We break it down to calcium oxide and carbon dioxide. Now, this calcium oxide is a basic oxide. Okay, it will react with silicon. You know, there's silicon as impurity. The silicon plus oxygen was silicon dioxide. So this calcium oxide is a basic oxide. We react with silicon dioxide, which is an acidic oxide, to form what we call calcium silicate. To form calcium silicate. This calcium silicate is a slag. Okay, it will melt as a molten slag and is floating on top of the molten iron. It's less dense than iron. The silicate, the slag floats on top of the iron, and the iron is collected at the bottom. This is reaction calcium oxide plus carbon dioxide to produce calcium silicate. Okay, so this is what happened in this case. Okay, so we can see for extended student, you need to be able to write it in symbolic equation form. Okay, for extended student, this is what is expected, not just word equation. Word equation is for core student, core. Those who are not taking science in the point, they're just doing combined science. Okay, in zone 1, this is what happens. We change the color. In zone 1, we have carbon react with oxygen to produce carbon dioxide gas in zone 1. This carbon dioxide react with more carbon, okay, a reduction reaction to produce carbon monoxide. In zone 3, carbon monoxide that you have produced react with the hematite, which is iron ore, to produce molten iron and carbon dioxide. You should learn how to balance the equation. It's very important if you are a studied student. Okay, so once you get the molten iron is dense, it flows down. Then there is some impurity. Carbon dioxide is removed, so carbon monoxide removed. They are gases. Anyone that is a gas will flow out as a waste gas, but there is still impurity that has not been able to be removed. Silicon dioxide. So first, the limestone is broken down because due to heat to calcium oxide. Calcium carbonate, which is the limestone, is broken down to calcium oxide and carbon dioxide. Now, this carbon dioxide is a wasteful gas, so it escapes as wasteful gas. Then this calcium oxide is a basic oxide, react with the acidic oxide. So a basic oxide reacts with acidic oxide to form calcium silicate. This calcium silicate is in a molten form. and is lighter than the iron, so it flows on top of the iron. So that's that for that. Now we're done with the extraction of iron. Now we go to the extraction of aluminum from bauxite. Okay, so before we do this, let's take a look at the tutorial. The extraction of aluminum from bauxite. Okay, we go to the extraction of aluminum from bauxite. Okay, so without much ado, let's see what this has for us.
This video is about how aluminium is extracted from bauxite. Aluminium is more reactive than carbon, so must be extracted using electrolysis. Unlike iron, it cannot be extracted using reduction via carbon or carbon monoxide. Bauxite contains aluminium oxide, and the process of electrolysis uses electricity to separate aluminium oxide, which is an ionic compound, into its elements, aluminium and oxygen. Only extended students need to know about how this process works and state the equations that occur. The main ore of aluminium is bauxite, which contains aluminium oxide, and this must be purified before it undergoes electrolysis. Aluminium oxide is an ionic compound, and in order to undergo electrolysis, it must be either molten or in solution. To reduce the melting point, the aluminium oxide is dissolved in cryolite. This lowers the required temperature from 2000 to 950 degrees Celsius. This electrolyte is placed into an electrolytic cell made of steel and lined with graphite. Graphite is used as it has a high melting point and can also conduct electricity. The graphite forms both electrodes, the cathode, which is negative, and the anode, which is positive. Molten aluminium is formed at the cathode where it is tapped off, and oxygen is formed at the anode. Extended students should know the reactions that occur at the cathode and anode and be able to give the half equations. At the cathode, reduction occurs. Positive aluminium ions in the electrolyte are attracted towards the negative cathode. The Al3+ ions gain electrons, so reduction occurs. Aluminium has a lower melting point than the electrolyte, so it will be molten and is tapped off. Negative oxygen ions in the electrolyte are attracted towards the anode. Here they lose electrons and oxygen gas is formed. This process is called oxidation, as electrons are lost. The overall equation for the reaction is aluminium oxide forming molten aluminium and oxygen gas. Given the high temperatures of this process, the oxygen produced actually reacts with the graphite anode, which is formed of carbon. The anode will begin to wear away, and therefore this will need to be replaced often. To remember which way round the reactions at the cathode and anode are, think of red cat, reduction at the cathode, and anox, oxidation at the anode. Let's now have a look at an exam-style question. This contains extended material. You have been asked to give 2 reasons why the aluminium oxide is dissolved in cryolite. Aluminium oxide is an ionic compound, so will have a high melting point. If it is to undergo electrolysis, it must be molten or in solution to allow the ions to move and carry a charge. So to gain both marks, you need to say that the cryolite will reduce the melting point of the aluminium oxide, and this will allow the aluminium oxide to conduct electricity. For part 2, you have been given an ionic half equation to complete. To balance this equation, it must be balanced for atoms and charge. There are 2 oxygen atoms on the right-hand side, so a 2 is needed on the left-hand side. This gains the first mark. As there are now 2 oxide ions on the left-hand side, the overall charge on the left-hand side is 4-, so we now need a 4 in front of the electrons. This will gain you the second mark. Finally, for part 3, you have been asked why the anode needs replacing frequently. If you remember, oxygen is formed at the anode, and the anode is made of graphite. Given the high temperature in the electrolytic cell, the carbon in the graphite and oxygen formed at the anode will react to form carbon dioxide. To gain the mark, you must say that carbon dioxide is formed. In summary, aluminium is extracted from purified bauxite via electrolysis as it is more reactive than carbon. Rhyolite is added to reduce the melting point of bauxite and also to dissolve it. This allows electrolysis to occur as the ions are free to move and carry a charge. The electrolytic cell is formed from a steel case which is lined with graphite. Reduction occurs at the cathode and molten aluminium is formed. Oxidation occurs at the anode and oxygen gas is formed. Extended students need to know the half equations that occur at the cathode and the anode. Don't forget to check out all our other fantastic revision resources.
Okay, so we've seen what is taking place or what is going on at the anode and at the cathode. There we said that this one for bauxite, it's by electrolysis. This aluminium, to obtain aluminium from bauxite is by electrolysis. Why? Because it's among the top most reactive elements in the reactivity series. Okay, if you among the top, if you are not below carbon in the reactivity series, if you are above carbon in the reactivity series, so you'll be extracted using electrolysis method. Those potassium, calcium, lithium, sodium, magnesium, aluminium, all of these ones, they are extracted using electrolysis method. Is that okay? So we don't extract them by reduction with carbon, like the one we did for iron just now. Iron, we are reacting with carbon, the coke. Okay, it's a reduction reaction with carbon. Even the carbon or carbon monoxide. So you could see we were extracting it using carbon monoxide reactive. So, but for this one, it's different. Okay, the first thing we do here, we purify the bauxite. Aluminium is a reactive metal, and it's above carbon. Once you are above carbon in the reactivity series, we cannot use the reduction method with carbon to do it. We have to use electrolysis method. Please take note for IGCSE, Cambridge IGCSE students. Once a metal is above carbon in the reactivity series, then we don't use reduction with carbon to carry it out to extract the metal. We use the electrolysis method. Now, so it's May ore, the May ore for aluminium. There are other ore, but the main one you study at this level is bauxite. The May ore where you find most aluminium is bauxite. There are other ore, okay? And this bauxite contains aluminium oxide, which is called the ore of aluminium. Contain aluminium oxide. Now, aluminium is higher in the reactivity series than carbon. We already established this. So if you are higher in the reactivity series than carbon, what it translates to is that you're going to be extracted using electrolysis method, not reduction with carbon method. So it cannot be extracted by the reduction of carbon or carbon monoxide. We cannot use the reduction method of carbon to obtain it. We have to use what? We have to use electrolysis method. So instead, aluminium is extracted by electrolysis. So you find this in multiple choice question. Which of the following methods can be extracted by electrolysis method? A, zinc. B, copper. C, silver. D, aluminium. The answer is aluminium. So we should know because why? Because aluminium is higher than carbon in the reactivity series. Now let's move on to the next one. The electrolysis of aluminium. Now how we do it? Aluminium, the bauxite, which is aluminium ore, is fed into this electrolysis compartment. Here we have the steel. This whole thing is a steel case to cover this. Why this is made of graphite? Okay, both the cathode, this is cathode. Okay, this type of electrolysis is a little bit different from the way we used to draw the electrolysis diagram. So you must know how the aluminium electrolysis works. Okay, this is a cathode. This whole plate is a cathode, and while these two edge, they are the anode. These two edge are the anode. It will be different from the previous way. Is that okay? Now, this place, this is where we have the purified, you must purify the bauxite, purified aluminum ore, dissolved in multi-cryolite, dissolved in multi-cryolite. Why do we have to dissolve the aluminum ore in multi-cryolite? Why do we have to dissolve the aluminum ore? Because aluminum is an ionic compound. Aluminum oxide is an ionic compound. So we need to, since it's an ionic compound, it has a very high melting point. It has a very high melting point. But if we dissolve it in multi-cryolite, it will help us to reduce the melting point of aluminum oxide. Okay, it will help us to reduce, because the temperature is around 2000 plus to melt it. And we cannot provide such temperature here. It will be too expensive to control and to use. So we dissolve in multi-cryolite to reduce the melting point from about 2000 to about 900 degrees Celsius. So we are able to reduce the melting point by dissolving the pure aluminum ore or aluminum oxide in the multi-cryolite. So please take note of why we dissolve aluminum in multi-cryolite. This can also come out in the exam. Why? We've seen it in previous exam. Why is the aluminum, and which state must the aluminum ore be? Must be in a purified state. The pure aluminum ore is dissolved in multi-cryolite to reduce the melting point of aluminum. Why we do that? Because aluminum oxide is an ionic compound which has higher melting point. Remember, ionic compound has high melting and high boiling point. So to reduce the melting point, we dissolve in multi-cryolite. Is that okay? So once it will ionize into ions. Now the ions you may find will be something like this: aluminum ion and oxygen ion, right? You have Al iron, Al3 plus. Remember we say it's an ionic compound. So when you dissolve in multi-cryolite, it will be in form of ion and oxygen ion. Okay, O2 minus. Now the positive ions, like this one, will migrate to the anode, to the cathode. The positive ions, like aluminum ion, will migrate to the cathode. And then they will, when they migrate to cathode, they will gain electron. So they will lose electron. Electron. So the equation at the cathode will be discussed later. We'll show the equation. Okay, because you have something like this. You have aluminum, 3 ion plus, okay, by gaining 3 electrons, flowing from the battery. Okay, the electrons, they are flowing from the battery coming to the cathode. So they will gain this electron and they will become aluminum multi or aluminum liquid. At this point, the aluminum is liquid. Because it's in a multi state. Aluminum is liquid because it's in a multi state at this point. Okay, so this is produced at the cathode. Okay, the aluminum you're looking for, you want to extract, is produced at the cathode. Okay, this is what happens at the cathode, cathodic equation. Now at the anode, the oxygen, this oxygen ion that is dissolved. You know, when you dissolve the iron 3 oxide in a multi-cryolite, it breaks into ion. This oxygen ion comes here, becomes oxygen 2 minus, lose electrons, sorry, eraser, just a moment, okay. O2, the oxygen gas, plus 4 electron. It loses this electron. Okay, so here we put 2 here at the back of this. Okay, so this oxygen migrates to the anode. This is the anodic equation. This oxygen ion migrates to the anode. And when they migrate to the anode, this equation occurs at the anode. Here is a reduction reaction at the cathode, and here is oxidation reaction at the anode. Okay, so we move on. Finish, you obtain your aluminum. Now let's take a look at the process of aluminum extraction by electrolysis. Now first, we feed the bauxite is first purified. Okay, remember that. Always remember that it's the pure bauxite that we will put in a multi-cryolite. The bauxite is first purified to produce aluminum oxide. We first purify the bauxite to produce aluminum oxide. Okay, the aluminum oxide is dissolved in a multi-cryolite. We already gave the reason because the melting point of because it's an ionic compound. Aluminum oxide is an ionic compound. It has a very high melting point, over 2000 degrees Celsius. Over 2000 degrees Celsius. This will be too expensive. It will be too expensive and a lot of waste of energy. So in order to make it suitable for us to be able to afford it, we find a way to reduce this temperature, the melting point of this. So to do that is to dissolve it in a multi-cryolite so that it can lower the melting point without interfering with the reaction. So the essence of the cryolite, multi-cryolite, is to reduce the melting point. Now the mixture is placed in an electrolytic cells or electrolysis cells like we have described, and graphite is used. They may ask you for electrolysis, which of the electrodes are, what is used as the electrode? The graphite. Graphite is used as the electrode. Both the anode and the cathode, we use the graphite electrode. Okay, now at the cathode, the negative electron, we already discussed what happens. Aluminium gain electron at the cathode. Aluminium gain electrons. This is a reduction reaction. We've written the equation, right? Which is this. We've written the equation. Aluminium gain electrons. The electrons are coming from the battery. They go to the negative terminal, which is called the cathode. And then this aluminum ion that migrated to the cathode gain these electrons coming from the battery, and then to become aluminum. Now at the anode, what happens is that the oxides, okay, oxides of oxygen, okay, at the cathode, the oxide ion lose electrons. When you lose electrons, you become oxidized. You become what? Oxidized. So oxidation is taking place at the anode. Now oxygen is produced at the anode. Oxygen gas is produced at the anode. So you can see the oxides lose electrons to become oxygen gas. Okay. Now the overall equation for the reaction is this. Now this is the overall. These are half equations. If they ask you to give the two, extended student for Cambridge IGCSE should be able to give these two half equations. What is happening at the cathode and what is happening at the anode. These half equations. We should be able to give them. Aluminum and oxygen gas is produced. Now the overall equation, if they need the overall equation is very easy. Overall equation, you have just to understand the concept. It is aluminum, the bauxite, the purified aluminum oxide that is decomposed into aluminum and oxygen. So you should be able to write the two products. This one breaks into aluminum from the cathode and oxygen from the anode. So you should be able to write the overall. If they ask you for the overall equation, you write this. The two half equation is this and this one. If they ask for only half equation, we write these two. If they ask for the overall equation, we write this. That's it. Now the carbon, there is a carbon. Graphite is a carbon. It's an allotrope of carbon. The carbon in the graphite anode react with the oxygen produced. Oxygen easily can react with carbon, right? Oxygen produced at the anode react with the carbon from the graphite, because remember we are using graphite as our electrode. Okay, so it reacts with this to produce carbon dioxide. So what happens is that the graphite is worn off. So they will ask you one question that can be asked: Why are we always replacing the graphite in the anode in the electrolysis of aluminum? Why? This is an exam question also. Why do we always replace? Because it's depleted, it's used. Why do we always replace? Because it's used. Why? Because oxygen is produced there. The oxygen that is produced at the anode reacts with the carbon from the graphite to produce carbon dioxide as a gas. So it's used up. It becomes a gas. It's used up. So as a result, the anode wears away and has to be replaced regularly. So this is a very big Cambridge IGCSE question. They can ask you, why do we always replace the graphite at the anode? Because the reason is because oxygen is produced at the anode by oxidation method. This oxygen that is produced by oxidation method react with the carbon from the graphite to produce carbon dioxide as a gas, and the gas will always escape. So it's always one off. So a lot of electricity is required for this process of extraction, and this is very expensive. So we have to always replace. Now, you need to know what is oxidation. Just a tip, exam tip. Oxidation means oil rig. Oxidation is loss of electron. That's the meaning of this oil. Oxidation, O is oxidation, I is lost, L is lost. Reduction means gain of electron. Anywhere electrons are gained is reduction reaction. Anywhere electron is lost is oxidation reaction. So oxidation is the loss of electron, while reduction is the gain of electron. So I hope we were able to break this aspect for you, and we thank you for joining us. We see you again in our next chapter. Thank you.